So today we're going to look at function operations and compositions of functions. So look at example 1. Actually, before we look at example 1, these are essentially the function operations that we're going to be working with. So the only one that's going to be difficult, or actually not really difficult, but has an additional step, is if you have a quotient. So if you end up with a fraction, remember you have to look at the restriction in the denominator because g of x here cannot equal 0. So whatever you end up with in the denominator, you have to set equal to 0 and solve so that you can write a restriction. The rest of these, if there's no fraction, there's no restriction. So look at example 1. I'm going to make this bigger so that I can work with it. Oh, that's really crooked. There we go. It's a little bit better. Okay, so for the first example, we're going to take the f function and add the g function to it. So I've got big parentheses, and then I'm going to take the f function, which is 3x squared plus 2x minus 4. So that's my f function. And then I'm going to put the g function over here. And then we just add them together. So I'm looking for like terms. When you add like terms, you just add the coefficients. The variable string stays the same. So 3x squared and 4x squared is 7x squared. So I took care of these. And then the 2x, there's no other term to go with the 2x. And then finally your constants, negative 4 and positive 8, would be a positive 4. All right. Now, the only difference between number 1 and number 2, these notations actually mean the same. We're still taking the f function and adding the g function to it. This does not mean to multiply this 2 into here at all. It doesn't mean multiplication at all. That means to substitute 2 into the sum . So you're going to substitute 2 into the sum of those two functions. So this is actually the sum of the two functions, so we could actually substitute the 2 into here. So if I took 2 and squared it, I get 4. 4 times 7 is 28. 2 subbed into here times 2 is 4. 28 plus 4 is 32, plus another 4 is 36. So the value of this when x is 2 is 36. So one of the ways that I could have done this was to actually find the sum of the f and g function and then plug that 2 into there. That actually takes longer. So if this were the problem that I had been given originally, I would have done the following instead. I would have found, first and foremost, f of 2. And so my f function is 3x squared plus 2. I'm going to have to move this over. I can see that right now. There we go. Plus 2, and then x, and then minus 4. So I'm going to plug in or substitute in a 2 in for every x. And so 2 squared is 4. So this 2 squared here is 4 times 3 is 12. And then 2 plus 2 is 4, and then minus 4. And so this value is equal to 12. So then step 2, now I'm going to find g of 2. So the g function is 4x squared plus 8. So I'm going to plug the 2 in where the x was. So 2 squared is 4. 4 times 4 is 16. 16 plus 8 is 24. And so then my third step would be f plus g of 2 is equal to the 12 plus the 24. And so that's going to equal 36. So my final answer is 36. And if you recall, isn't that the same value we got when we plugged 2 into here? So this tends to be easier math to do it this way, and the only time I do it this way is if I actually have a number to plug in for the variable. So remember that, trying to figure out what color I want to use, f of x plus g of x is exactly the same as f plus g of x. So this does not mean multiplication. All right, so let's look at subtraction. I still want to be able to see my functions. All right, so we're going to do f minus g of x. So it's highly important that you use substitution parentheses. So I am going to use big parentheses minus big parentheses. So I'm going to plug in the f function first, which is, because it comes first, 3x squared plus 2x minus the 4. Then I'm going to plug in the g function because it comes second, 4x squared plus 8. Then collect like terms, except there is a reason for this negative to be here. It is really important that you distribute it all the way. If you don't use substitution parentheses, you're going to only end up subtracting the 4x squared. You're not going to end up changing the sign of this 8, and it has to be a negative 8. So we end up with 3x squared plus the 2x minus the 4, and then when you distribute this negative, you get a negative 4x squared. And when you distribute the negative here, you get a negative 8. Now we can collect like terms. So 3x squared minus 4x squared, that's going to give us a negative 1x squared. And so I've used this one and this one. Then my next highest degree term is my x term, and there are no other x terms. So I'm just going to write down positive 2x. And so then I use that one. And then finally my constants, negative 4 and negative 8, give me negative 12. So then my final answer is this. So this is f minus g of x. So then what I would like you to do is pause the video, and I want you to find g minus f of x. So the g function is going to come first, minus the f function. Make sure you use substitution parentheses. So pause the video and then restart it. All right, so I am going to use substitution parentheses. So big parentheses minus big parentheses. So I'm going to take the g function first, which is 4x squared plus the 8, and I'm going to put in the f function next, which is 3x squared plus the 2x minus the 4. So remember that we have to distribute this negative all the way to all those terms. So we end up with 4x squared plus 8. Distribute your negative. Negative times 3x squared is negative 3x squared. Negative times 2x is negative 2x. And finally, a negative times a negative 4 is a positive 4. Now we're just collecting like terms. So 4x squared and a minus 3x squared. 4 minus 3 is 1. So we get a 1x squared. And then I used these two, so they're gone. Then my next highest degree term is this negative 2x, and it doesn't have any other like term, so minus a 2x. And then I use this. And then finally my constants, a positive 8 and a positive 4, they are going to combine and give me a positive 12. And so now I use these two, and our final answer is this. Notice that when you have f minus g of x and g minus f of x, we got exactly the same thing, except for every sign is the opposite sign. Notice all of these are all the opposite signs here, and let's get this last one. There we go. All right, so then let's look at our next page. So now we're going to multiply and divide functions. So let me make this bigger. There we go. Okay, so again, you could have written, instead of f of x times, and notice that that's a closed circle. If it's open, it means a composition, times g of x. This could have been written as f times g of x. They both mean the same thing. So I'm going to take the f function, which is x squared, and I'm going to multiply it to the g function. So I'm going to distribute this x all the way through. When you multiply like bases, you add the exponents. So x squared times x gives you x cubed, and x squared times negative 3 is negative 3x squared. That's it. It's that easy. All right, so then the second one is f times g of 2. Well, this is f times g, so again, theoretically, we could plug the 2 into here, into both of those x's, and evaluate. So if I take that 2 and substitute it in here, 2 cubed is 8. Substitute it in here, 2 squared is 4, times 3 is 12. So 8 minus 12 is negative 4. So you could do that. You could find the product of those functions first and then sub in the value. Well, an easier way, if this had been my original problem and I hadn't done this, an easier way would be to do the following. So I would start off with finding f of 2. And so my f function is just x squared. So I'm going to put a 2 in for there, and I very simply get the answer of 4. Then my second step is going to be to find g of 2. And so my g function is x minus 3. My x is 2, so 2 minus 3 is negative 1. So then my third step would be to find f times g. Well, if my f is 4 and the value of my g function is negative 1 when x is 2, then I just have to multiply those together. And so if you recall, we got negative 4 when we plugged it in over here. So either way gets you the same answer. All right, so now we're going to do division, and division has a little bit of a different animal, and so you've got two different functions here than we had with a multiplication. So we're going to take f divided by g and g divided by f. So remember, when we divide, we have to look for a restricted domain. So I'm just going to take the f function and divide it by the g function. So the f function is x squared plus 2x cubed, all divided by x squared. Then you have to factor the numerator, and the denominator is a monomial, so it can't be factored. A lot of you are going to want to try to cancel these x squareds. You cannot cancel or reduce when you have addition or subtraction signs outside of parentheses. You just can't do that. So I'm going to have to factor this numerator. The only thing I can factor in the numerator is a greatest common factor. So I'm going to factor out in x squared, out in front of parentheses. So technically, I'm dividing this by x squared and this by x squared. So x squared divided by x squared is not nothing. It is 1. Anything divided by itself is 1. So we're going to get a 1 here. And then the 2 doesn't disappear, so we have a plus. Oopsies. Let me erase that. Try that again. So I've got a plus 2. And then x cubed divided by x squared, when you're dividing like bases, you subtract the exponents. So 3 minus 2 is 1. So I have 1 plus 2x. And then it's all over x squared. Now that I have all addition and subtraction inside of parentheses, now I can cancel these two. So the x squared cancels with the x squared, and you are left with 1 plus 2x. So there's your answer, but we have restrictions. So notice that we have x squared in the denominator. That denominator is not allowed to be 0. So what value would x have to be to create a 0 in the denominator? If x were 0 and you square it, you're going to get 0 in the denominator. So we have to add a restriction to our answer that x cannot equal 0. And that becomes your final answer. So then I want you to pause the video and I want you to find g divided by f. We've already done the factoring, that so it shouldn't be different, and then I want you to see if you can figure out the restriction on the domain. So pause the video. Okay, so as I'm looking at number 2, I'm going to take my g function, which is x squared, divided by my f function, which is x squared plus 2x cubed. So then you're going to have to factor the numerator, which we can't, and factor the denominator, which we just did on the other one, so I'm not going to explain that again. So we got 1 plus 2x. And of course, just like before, you can cancel these, but unlike before, if everything cancels in the numerator, you have to replace it with 1. So we end up with 1 over 1 plus 2x. We still have to do restrictions on the denominator, but this time I have an x squared in the denominator and a 1 plus 2x. So you have to take your original factor denominator, even though you canceled out the x squared, you have to look at the original factor denominator and make your restrictions. So domain restrictions. Okay, so your first restriction is going to be the x squared cannot equal 0. So remember, we already said with that one that x cannot be 0. So we're going to tack that on to our answer here, but we're going to have a second one. And then for the second one, you've got to set this 1 plus 2x not equal to 0. 1 plus 2x not equal to 0. Solve for x, so we would subtract 1 and divide by 2. So we're going to add that x cannot equal negative 1/2 either. And then this becomes, all of this is our final answer. All right, so let's look at your definition of composition of two functions. So essentially, if you're finding the composition of two functions, if you remember, that's Fogg and Goff from Algebra 2. So Fogg is just f of g of x. You're going to take the g function and substitute it into the f function. So these are written in two different formats. This one actually looks like and makes sense of what we're doing. So we're going to take, this used to be f of x, but instead of f of x, we've got g of x in there. So we're just taking g of x and substituting it into the f function wherever you see a variable. The other thing that's important is this right here, which we're going to talk about more in a minute. It doesn't make a lot of sense right now, but basically when you have a composition, you're going to have to find the domain of your f function, find the domain of your g function separately. If either one of these two are restricted, then your composition is going to, the domain of the composition is going to be the most restricted domain of the two of these. Okay, so look at example 3. So really, a composition is just putting one function inside of another function. So I have two very basic functions, and as you look at number 1, you are to find f of g of x, and then find f of g of 2. We're going to look at these as two different problems. What would I do if I had this versus what would I do if I had this? So let's ignore this for right now because this is actually an easier problem than this one here. Let's just find f of g of x. So we're going to take the g function here and plug it into the f function. So this is on the outside, so it drives what's happening. So we're going to take, since this is on the outside, we're going to take the f function. So we have f of g of x equals, so we're going to take Hopefully I didn't mute you for very long because apparently I hit the mute button. Sorry about that. Sorry. All right, so something plus 1. So I'm going to put the 2 into here. So 2 plus 1 is 3. So then our second step is going to be to find f of this value here is going to go in here, so f of 3. So we're not plugging 2 into both of them because it's a composition. So our f function is just x squared, and so then the 3 gets plugged in here, and then you end up with 9. And didn't we say that we were going to get 9 here when we plugged it in? And we surely did. All right, so last problem on this page. We're going to find g of f of x. So I want you to pause the video, and I want you to find g of f of x. If you recall, this is the same as g of f of x. So all you have to do is take the f function and substitute it into the g function. So the f function gets subs into the g function. So pause the video, do it, and then restart it. So if I find g of f of x, I'm going to start with the g function because it's on the outside, and I've got something plus 1. And then inside the g function, I'm going to put the f function, which is x squared. So there's nothing for me to do here, so I can drop the parentheses, and then my final answer is going to be x squared plus 1. Now let's talk about the domain of each of these functions. So the domain on this function right here normally would be unrestricted, negative infinity to positive infinity, but you have to look at the domain here and the domain here. This is unrestricted. It's not in a fraction, it's not underneath a radical. So the domain here is negative infinity to positive infinity. Same thing here, this domain is unrestricted. It's not in the bottom of a fraction, it's not underneath a radical. So both of these are negative infinity to positive infinity for the domain. So then our domain for our composition will also be negative infinity to positive infinity. And so the same thing is going to occur here because we've already looked at these separate domains. It doesn't really matter here because these domains, I mean, I guess you could have ended up with a restricted domain here, but we didn't. This is unrestricted, this is unrestricted, this is unrestricted. So again, just like example 1, our domain on this composition will also be negative infinity to positive infinity. Then let's look at our last page of notes. All right, so let's make this bigger. Okay, so we are going to break composition functions into simpler functions. So you're going to start, you're going to really work your way backwards. This right here is going to represent f of g of x. And so that's what this is saying here. H is f of g of x. So we have to figure out what's the f function and what's the g function. So the easiest way to figure that out is to look to see what the parent function is. F is going to represent the parent function, the bigger function. G is going to represent what's being substituted in to the big parent function. So this is typically smaller, and this is typically bigger. I like to look, to find G, I like to look inside of parentheses, underneath a square root, or inside absolute values. Those are the things that we tend to plug into. So see how we have parentheses here? So if I highlight this right here, and in fact let me highlight that with pink. So only the x minus 2 has been substituted in to here. So if I cover up the x minus 2, you have 1 over something squared. So that 1 over something squared becomes your f function, and it's 1 over x squared. Then this thing that we highlighted inside here, the part that's inside the parentheses, that becomes our g function. So there's our g function. And so now we have split 1 over x minus 2 squared into our two separate functions. So we broke them apart. Look at the next one, this one right here. So here's where your parentheses are. This is the part that's been subbed in. So this is the part that's in parentheses, so it must be our g function, which it certainly is. If you cover that up, you're going to replace that whole thing I just highlighted in pink with an x. So you have 1 over, cover that up, x cubed plus 1. Oh, there is a typo here, so please make sure you change this to a 4. Somehow that got missed, so this should be a 4. So now you have a 4 over, cover that up, x cubed plus 1. So that's how we got 4 over x cubed plus 1. So essentially, whatever is in oh, it's not what I wanted. Try a highlighter. Whatever is in parentheses can be your g of x, and we're basically going backwards. All right, last problem. Now we talked a little bit about finding the domain of a composite function when your original functions are restricted. So this time, this function is not restricted. It's not underneath in the denominator of a fraction. It's not underneath a radical. But notice how this is underneath a radical. So it is restricted. Well, the question is, how do they get this? So remember, whatever is underneath here, so let me highlight that. So this part that's underneath here, that has to be greater than or equal to 0. Because you can only take the square root of a positive number. So we're going to take the 9 minus x squared, and we're going to set it greater than or equal to 0 and solve. So we're going to subtract 9. We get negative x squared greater than or equal to negative 9. And then we are going to multiply this side by negative, multiply this side by negative, and when you multiply both sides by negative, remember on an inequality, that flips. So you end up with x squared less than or equal to positive 9. Now, normally we would take the square root of both sides and plus or minus the square root here. So you end up with an answer where x is less than or equal to positive or negative 3. For a lot of you, that's going to be difficult for you to figure out, how do I get this set notation? So take your boundary points, and positive and negative 3 are your boundary points. Put them on a number line. To figure out what it should be, we're going to take some test points. We're going to choose a value in between negative 3 and 3 and test it in here to see if it's true or false. Take a value here and a value here. So one of my favorite test points is 0, so I'm going to choose 0. And then I want to choose a value that's bigger than 3, that when squared and subtracted from 9 gives you a perfect square. So I'm going to choose 5, because 4 doesn't work, but trust me, 5 does. So I'm going to choose like 5 and negative 5. Those are my 3 test points. So let's start with negative 5. Negative 5 times negative 5 is positive 25. 9 minus positive 25 is a negative 16. So that's false. I can't take the square root of a negative number. Then let's test 0. Put 0 in here. 0 squared is 0. 9 minus 0 is 9. I can take the square root of 9. That's 3. So this is true. Then let's test positive 5. Positive 5 squared is 25. 9 minus 25 is negative 16. So again, I cannot take the square root of a negative number, so that's false. So what that means is I only want values between negative 3 and 3 and including them. So I want to go from negative 3 to 3 and include them, so we have brackets. So this is restricted, this is not. So what happens when we find the composition? So go ahead and find fog, pause the video. You're going to take the f function, or actually you're going to take the g function and plug it into the f function. The g function gets plugged into, substituted into the f function. So pause the video and find that composition. So I'm going to take my f function, and I'm going to take this g function, and I'm going to put it right in here, square root of 9 minus x squared. Anytime I take a radical and square it, I'm going to get the number underneath the radical, so I get 9 minus x squared minus 9. the 9 and negative 9 cancel, and I end up with negative x squared. So my f of g of x is equal to negative x squared. So what's the domain? Well, normally the domain of this would be unrestricted, but the problem is we put a restricted function into original function. So we always have to look at our original function before it was ever simplified. So because this is a restriction here, and this is more restricted than not restricted, this becomes our domain. So all of this becomes my answer. If I were to graph negative x squared, which is a parabola that opens down, I would only be able to graph points on negative x squared from negative 3 to 3. So I would not have an arrow on both ends of my graph. I would plug in negative 3, 3, and a few other points in between, and those are the only points that I would be able to graph. And so that is it. I have assigned you some homework out of your textbook, so go ahead and try that. If you have questions, please give me a holler. Come see me. Have a great day.